And for my last trick in Unit E, let's take a look at Objective E7, which will be looking at proportions, and more specifically, direct versus indirect variation. So proportions are going to be two ratios that are equal. So for example, 3/4 and 6/8. Those are equal proportions. Because 1/4 is equivalent to 2/8, so 3/4 would be the same as 6/8. It's any two ratios we can set equal to each other, and these proportions can most easily be solved with some sort of a cross product or cross multiplication. The example here, A over B equals C over D, we can cross multiply to get AD equals BC. So that cross multiplication usually works by looking at this cross. Where I multiply the numerator of one side with the denominator of the other side, and then get to set them equal. So if we're going to take that example at the top and rewrite each of those proportions as their cross product, or just cross multiply them, then for 3/4 over 6/8, I'm going to get 3 times 8 equals 4 times 6. 3 times 8 is 24, and 4 times 6 is 24. Roughly, that's going to be cross multiplication. If I keep working through those examples, I've got 6 times 40x equals 8 times 30x, which in both cases gives me 240x. So those are ones where we're using the same variable, so we can easily see that I get an identity, being that both sides of the equal sign are the exact same thing. The next one over, x over y, equals 2 over 3. Well, that's 3x equals 2y if I cross multiply. Now I've got two different parameters or two different variables here. So I've got a way to relate x and y together. Still a valid proportion though, because I know that x over y must be equal to 2 over 3. One more time on that last end, if I cross multiply, 5x equals 6 times x plus 2, right? X times 5 and 2 times 3 times x plus 2. And then that could be simplified from there. But for the most part, I just want to focus on the cross multiplication idea. So clearly, I can solve that rightmost example for x. But to try this out on an older problem from all the way back in lesson 13, we had an example that said that sound travels at 125 feet per second. How long does it take for the sound to reach a person on the ground from a height of 135 feet? Well, I can set up a proportion here, a ratio that works. I know that I have 125 feet per second, or 1,125 feet per second. It should be equal to feet over seconds. So this will be 135 feet over however long it takes. The equation here from physics is that velocity is equal to distance over time. And I can see that just by looking at the units. Velocity, which is in feet per second, or maybe miles per hour, or meters per second. I can pick any velocity unit I like, but it's equal to some distance, being feet, meters, or miles, over time, seconds, minutes, or hours. And the proportion that I can set up to get that equation equal on both sides can be obtained just kind of by looking at our units. So 1,125 feet per second should be equal to feet over seconds. And then I can, in turn, cross multiply that thing. Because don't forget, 125, it's really just 125 over 1. So I can cross multiply to get 1,125. T is equal to 135 times 1. So the time it takes is 135 over 1,125. Slide that up just a little bit. So if I were to try and describe the relationship between velocity and distance and time, well, I could say that the velocity directly varies with how far the thing travels, but it is inversely proportional to how long it takes. And that's going to be our basis for direct variation and indirect variation. If y varies directly with x, or y is directly proportional to x, that means if I were to set up some kind of an equation that relates y and x together, they would both be in the same part of the fraction. So if y and x vary directly, it means if I'm setting up some sort of proportion, both of those values should go into a numerator. They'll be on opposite sides of the equal sign, but they'd both go into the numerator part, as opposed to the opposite of this, which will be indirect or inversely proportional. We'll see that they'll end up on opposite sides in the equal sign, but also in opposite sides of numerator and denominator. So when I say that time varies indirectly with velocity, that means velocity and time on opposite sides of the equal sign, and uh, the time ends up in the denominator, whereas velocity was in the numerator. This one's probably just going to make more sense if we go to look at examples. Let's go do that. For each of the following, we want to pick out the ones that could represent direct variation and explain why. So, starting by getting rid of a few things that don't. This curved line over here, direct variation is linear. So we're going to ignore that. Is that true, though? Think about that for a moment. If it's just those two quantities varying directly, then we won't see a quadratic shape like this occur. So I think I do want to stick with, for right now, direct variation is going to be linear, but we will look at some examples later where something can vary. So like the area, for example, of a circle is going to vary directly with the square of the radius. As you know, if the radius of a circle doubles, the area of that circle will quadruple because 2 squared is 4. So the radius is doubling, the area quadruples because it affects 2 dimensions. So let's maybe leave a question mark on that one for right now. One that I know is definitely not direct variation is going to be this one out here on the end, the one that has a negative slope. This is actually going to be an example of indirect variation. As x gets bigger, y gets smaller, and the reverse is true. Best example for what direct variation looks like is this linear graph right here. It's going to have a positive slope, and direct variation also needs to pass through the origin. If two values vary directly, then if one of them is 0, the other must be 0 as well. So this guy is not direct variation because it doesn't pass through the origin. Few other examples. What else do we want to say? If tuition at ABC University is $400 plus $300 per credit hour, that's going to not be direct variation because there is no slope. That $400 fixed cost makes it not direct variation. But if it were just $300 per credit hour, then it would be. Amanda's making 15% commission on her sales. That is direct variation. The more sales Amanda makes, the larger her commission will be. Direct variation. As one goes up, so does the other. For the ones below, I'm just looking for things that have a y-intercept of 0. Oh, which actually means that this one's okay if I solve that out. Because that'll really just be y equals 2x. So that one's cool. Y and x vary directly, but the other one, not so much. We'll get a y-intercept over there, so it's out. So for example 4, write a direct variation equation for each statement below. Distance driven varies directly with the speed of the vehicle. So distance is directly proportional to the speed or the rate, or maybe the velocity. I'll use v for velocity. Right, so they are directly proportional. One varies directly with the other, but we need some sort of proportionality constant, which is where we're going to introduce this idea of k. It's pretty similar to slope. There's just some constant that relates to ideas. A decent example of what this might look like as, say, something like distance in feet varies directly with distance in yards. Both of these are measuring the same distance, but one is measuring it in feet and the other is measuring it in yards. So that equation might look something like F equals K times Y. Let me actually write it the other way. Y for yards is equal to K times F. No, I had it right the first time. Shouldn't go doubting myself like that. My distance in feet is directly proportional to my distance in yards, and there is some proportionality constant between the two. I know that there are 3 feet in a yard, so my number of feet is going to be equal to 3 times my number in yards. If I've gone 10 yards, that's 30 feet. So F is equal to 3 times the number of yards. This proportionality constant just tells me how, first, that the two ideas are directly related to each other, but also it tells me that there's some sort of factor that changes the number between the two. So some proportionality constant that just makes it so that uh, the two numbers aren't exactly equal, they're just proportional to each other. After that, a circumference of a circle varies directly with its radius. Well, that'll be C equals KR. Circumference is equal to K times the radius. In particular, we happen to know this one. The circumference is equal to 2 pi r. So K here is 2 pi, just some constant that relates the two numbers together. It's important that this constant does not change. It's always a fixed number, but it lets me convert one number to the other. Now, and then here's another one I talked about earlier. The area of a circle varies directly with the square of its radius. So A is equal to K times R squared. A and R squared are directly proportional. And again, I know what K is in this one because area is pi R squared. So example number 5, suppose Y varies directly as X and Y is 45 when X is 3. Find Y when X is 12. Now, my favorite way to have done this, because we can kind of skip the formula step, so I'm going to look at it both ways. But I can see that X goes from 3 up to 12. X quadruples. It increases by a factor of 4, which means Y is also going to increase by a factor of 4. So if I look at 45 times 4, I'll get 180. So that should be my new answer. Following the steps that make this equation work with the proportionality constant might look something like this. Write an equation to solve for that thing. Well, it's going to be y equals kx. Y and x are directly proportional. Y varies directly with x, which means that 45 is equal to k times 3. And since k is a constant, I know that that constant must be 9. Y is always 9 times bigger than 3. So if I plug that in to get the equation, y equals 9x, since I now know what my proportionality constant is, I can then plug in 12 and figure out y. It'll be 9 times 12, which is 180. Is that right? Hang on a minute. Hang on a minute. Something's gone terribly wrong. And maybe you've already caught my mistake. Uh, 45 divided by 5 is 9, but 45 divided by 3 is 15. I am not very good with numbers, it turns out. So let's try again. Knowing now that our k is 15 and not 9, that means that y is always 15 times bigger than x, which makes a lot more sense. 3 times 15 is 45. So again, y is 15x. Now plug in 12 for x, and I do indeed now get that y is 180. Dodged a bullet there. All right, cool. So that's direct variation. We're gonna try this idea again. Volume of blood in human body varies directly with the weight. So that means we've got an equation. B is equal to KW. Then we say a person that weighs 160 pounds has approximately 5 quarts of blood. Find the constant of variation and then write that equation together. Well, that means 160 is equal to K times 5. Divide that over to the other side. 5 goes into 160 36 times? 32 times. There we go. So our constant of variation is 32. That means that a human is expected to weigh 32 times the number of quarts of blood that it has, or that he or she has. It's a person after all. So B is equal to 32W. So the constant of variation is 32 pounds per quart. We can attach some units to these things, because that occasionally is can be helpful. Yep, so that constant of variation, 32 pounds per quart. Let me just write that down. K is 32 pounds per quart. So estimate the number of quarts of blood in a person who weighs 220 pounds. Well, I can plug that in for, oh no, I've done this all wrong again. Because I've plugged everything in the wrong spot. How could I? Okay. Let me just try this equation over again. Actually, no, I'm gonna leave this here for a second so I can talk about what I did wrong and how I know I was wrong. Uh, it's not that all of it was wrong. I just plugged the numbers into the wrong place. This should have been 5 quarts of blood equal to K times the weight, which was 160. Meaning that K is actually 1 over 32. So if I bring this thing back, our quarts of blood, or volume of blood in the body should be about 1 over 32 times the weight. So maybe I even want to call this the weight divided by 32. So I just plugged my numbers into the wrong side was all, which means that K is actually not 32 pounds per quart, but is instead 1 over 32 quarts per pound. There we go. So if we try this thing again, estimate the number of quarts of blood in a person who weighs 220 pounds. Well, this will be B is going to be equal to 220 divided by 32. And pop that into a calculator real quick to see what we get. 220 over 32, 6.875. And that'll be quarts. Well, this is QT for quart, I think. All right, now solve the problem using ratios and proportions. So I think the idea here is that we could have set up an equation that might look something like the following. I could take person A, who had 6 quarts and 160 pounds, and set it equal to my unknown number of quarts per 220 pounds. And then I could solve this by cross multiplying. So this is the solving the problem with proportions instead of the direct variation equation. Similar to the previous one where I saw that x was going to quadruple so that I knew that y needed to quadruple as well. It'll be the same idea here. Solve this thing for b, I should cross multiply. So 6 times 220 is equal to 160b. And then to solve for b, divide 160 over to the other side. Do I want to do 6 times 220? Might as well, right? 1,320. Yeah, let's move this over here where I've got space. No, I lied. 1,320. We'll just make some space by sliding this up. Maybe sliding that up a little bit too. Over 160 is equal to b. And then I can see if I divide that number by 160, I'm going to get the same number. Why did I get a different number when I plugged that into my calculator? Did I calculate K wrong? That went fine. Because I have no idea where I pulled that 6 from. You're probably watching this video wondering what the heck I'm doing. Yeah, I have no idea where that 6 came from either. Should have been a 5. This is 1,110 over 160. Man, today's just not my day. I am really not very good with numbers. No, but anyway, I can see if I plug that into my calculator, I get the same thing, 6.875. Where I originally pulled that 6 from, I do not know. I guess there's a 6 in 160. Yeah, yeah, I don't know. So if I were to start that problem over and say where I got this thing from, I would set up my proportions. There are 5 quarts in a person who weighs 160 pounds and an unknown number of quarts in a person who weighs 220, and I want to solve for that unknown b. There we go. All right, indirect variation, or y is inversely proportional to x. Same idea. I'm going to set them on opposite sides of the equation, except now uh, one needs to be in the denominator. If two things are indirectly varying, it means that their product is equal to some constant value, but as one goes up, the other must go down. So if I just write some equations over here, the intensity of light varies inversely with the square of the distance from the source. That intensity, I, is equal to k times 1 over the square of the distance, 1 over distance squared. I and distance squared are inversely proportional. And C varies indirectly with the sum of A and B. C is equal to K times 1 over A plus B. C is inversely related or indirectly proportional to the sum of A and B. So Boyle's law, which I think is also known as the ideal gas law. In a closed container with constant temperature, pressure of a gas varies inversely with its volume. So let's check that out. Pressure is indirectly related or varies inversely with its volume. P is equal to K times 1 over V. Or maybe we'll just call that P equals K over V. Now, if I want to solve that thing for K, K is equal to P times V, which is 200 times 55, or 11000. Just 3 zeros, actually. Yeah, that looks about right. So that means if I wanted to rewrite the equation, I could say that the pressure is equal to 111,000 over the volume. So use your variation equation to determine the pressure when the piston is going to increase the volume to 165 cubic inches. So then our pressure will be 11,000 divided by 165, and toss that into a calculator. I got 66 and 2/3. And this, I think, is in PSI. Yep. Pounds per square inch. Right, number 9, sound intensity varies inversely with the square of the distance between the sound. So we can again set up our equation. Intensity is equal to K over D squared. So if you are in a movie theater and you change your seat to one that is twice as far away from the speakers, how does the new sound intensity compare to our original seat? So let's try this out. I2, our second sound intensity, I2 is equal to K over 2D squared, because we're going to double the distance away that we go. So this is going to look like K over 4D squared, the initial intensity. So this is 1 over 4 times I1. K over D squared being I1, K over 2D squared being I2. So the second intensity is only a quarter of the original intensity. So if we double our distance away, our intensity will change by a factor of 1 over 4, since that distance would get squared. Doubling that distance should create some sort of factor of 4 on the intensity. And because they are indirectly varied, I'm going to divide the new intensity by 4 instead of multiplying by 4. So next example, y varies inversely with the square root of x. So I could set up an equation, y equals k over root x. And I want to find y when x is 100. So if I set this up to find my, well, if x is going to get 4 times as big, y is going to become half as big. So y is going to end up being 3. So if I just look at this 4 times magnification here from 25 up to 100, I know that x got 4 times as big. Y varies inversely with the square root of that. Square root of 4 is 2. Inversely means 1 over 2. And half of 6 is 3. So that's where I'm just jumping right to the answer. A way of solving for that would be to say that k is equal to y times the square root of x, which is equal to 6 times 5. Square root of 25 being 5 for real this time, and it's 30. So if y is equal to 30 over square root x, this will be 30 over square root 100, which is 30 over 10, or 3. Now, joint variation just lets us talk about an object that's going to vary with more than one thing. So if I want to say that y varies jointly with x and z, then y is equal to some still variation constant k times x times z. And we can also have some combined variation, where we might have things varying jointly and inversely. So an example here, uh, if y varies jointly with x and z and inversely with the square of w, then x and z go into the numerator, while w squared goes into the denominator. So some examples where we write that stuff down. If interest is going to vary jointly with the rate of interest and the length of time on deposit, the interest earned is equal to K times RT. It's going to vary directly with both the rate and the time. If the rate goes up, the interest goes up. And if the time goes up, the interest goes up. We want to say horsepower varies jointly with the number of cylinders in the engine and the square of the diameter of the cylinder. Then that horsepower, I'll use P for power, is equal to some constant of variation K times my number of cylinders N and the square root of the diameter D. Look, if I've got the next one. The length of time it takes to build a highway varies directly with the length, but inversely with the number of workers. P is equal to K times L over N. Right? The longer the highway is, the more time it will take to build. But if I have more people working on the highway, it should take less time to build. So both factors can play into how long it'll take to build the highway. Both longer roads and fewer workers lead to more time, but shorter roads and more workers will lead to less time. All right, and electrical resistance in a copper wire varies directly with its length and inversely with the square of the diameter of its wire. That should look like K times L for length over square root D. Ooh, wait, nope, not square root D. D squared for diameter. Directly with the length and inversely square the diameter. So if I have a longer wire, it'll have more resistance. But if I have a wider wire, it'll have less resistance. There's more room for that current to run through. All right, and one last example to rule them all here. Body mass index takes both weight and height into account when assessing whether an individual is over or underweight. BMI varies directly as body weight and inversely with the square of height. So let's write down an equation. BMI, body mass index, is equal to K times, well, we're going to vary directly with weight and inversely with the square of height. So if I want to figure out what K is, we need some data point over here to solve for it. A person who's 180 pounds and 5 feet tall has a BMI of 35.15. If I plug all of those points in at once, 35.15, 180, and 5, I can solve for K. 35.15 is equal to K times 180 over 5 squared. But hang on, be careful here. Read the question a little bit more carefully. Varies directly with body weight in pounds and inversely with the square of body height in inches. So a person who is 5 feet tall is really 60 inches. So that means that K, 35.15 times 60 squared divided by 180. And we can plug that into a calculator. Ooh, and I got just a heck of a number over here. No, I didn't. I missed a division sign. I accidentally put multiplication instead of division in that last step. I got 703. Much more reasonable number. So that means that BMI equation, BMI, is 703 times W over H squared. So I want to find the BMI for a 170 pound person who is 5'10". So this will be 703 times our new number. 170 for weight, 510 for height. So 170 up top. A person who is 5'10" is 70 inches tall. So 170 over 70 times 703. I get a BMI of 24.39. And this is BMI the whole time. BMI, BMI. Right, and that's E5.